Good afternoon, everybody. Thanks for the wonderful opportunity to come here. I've met a lot of you in the last day and a half, and it's been incredibly exciting and impressive to see the broad range of activities in the department. A lot of really exciting stuff, and I look forward to meeting the rest of you over the next day and a half that I'm going through the process. And I want to thank Bob and the rest of the committee for organizing what was no doubt a very complicated logistical environment. So. I want to first start by just acknowledging a couple of the people I work with. So I do collaborate with a lot of people at NREL who are vital to my activities, and I benefit a lot from interactions. One is Joe Barry, who's sitting in the audience. But a whole slew of people work in Basic Sciences Center, Nikos Kopidakis, Andrew Ferguson, just mentioned a few, Yael van der Lagemout, who's part of the RACI Center, Gary Rumbles, part of the RACI Center. And then on the little more applied side of things, there's Joe Barry, as I mentioned, Dana Olson, Dave Ginley, Peter Graff, Brad McLeod, Sarah Cowan. Work very closely with these people and benefit quite a bit. Have a number of grad students that I also benefit very much from. Alex Dixon, Xinjiang, Robert Naraki, who's in the audience. He's in the back there. I'm going to show some of his data very soon. And Daniel Weingarten, who's in the physics department here at CU. And Dan Dessau has been kind enough to let me help mentor Daniel in his efforts. Of course, work with a number of people here at CU and also some groups at School of Mines. Before I begin with the formal lecture, I just want to give you an overview of sort of the broad perspective that I'd like to take in my research. And sort of falls into two categories. The main one is organic solar cells. That'll be the topic of the presentation. And that's really my bread and butter. I don't know, that's 70% of my intellectual effort so far. And in that area, I work on fundamental thermodynamic questions that I'll discuss today. Work on charge transport issues, measurement and theory, and device physics that I'll also talk about, and some processing issues. And work on a little bit of new molecular development with chemists who synthesize some very exciting molecules. On the other side, a little more of my emerging interests are in the areas of complexity, particularly in biological systems, and both systems that are actual biological systems and those that are engineering but inspired by biology. Let me give you just a quick set of examples. So one thing we do is grow bacteria in our lab in Denver in the physics department. It's kind of a new thing, but a lot of physics departments are working with bacteria. And what we're doing is growing these under stressed conditions on an agar plate, and they grow into fractal structures. It turns out that a fractal structure gives them the most efficient way to absorb nutrients as they travel across the surface of a film. Here's a few microscope images actually taken by Robert here in the CNL laboratory, as a matter of fact. And you see the edge of what is a bacteria colony, kind of looks like the boot of Italy. And as you zoom in a little bit to 20 times and then 50 times magnification, can we actually turn off this light? Because I think what you see is kind of a self-similar structure. So we're able to induce a fractal growth, structure growth into the bacteria. And we think this might have, first of all, it's fundamentally interesting from an applied math standpoint, but there might be engineering applications for such a structured colony. And then more on the more specific engineering side, we're working on a very new field called organic neuromorphic electronics. The idea is to use organic semiconductors as the medium for hardware implemented neural networks. And as far as we know, we're the only group in the world working on this. And we have some of the first designs to do this. So this is one of Robert's designs right here, which incorporates some bistable memory elements that'll be the weights of the neuron, and an OFET that would be the soma, the body of the neuron, to add up the weights. So that's just one, that would be one synthetic neuron. And Robert has used the CNL laboratory just a few blocks away here, a few floors away, to make a circuit that would combine 3 or more of these neurons into some kind of very simple neuromorphic circuit. And he's started fabricating that. Here is a picture of his design that has been photolithography created. As far as we know, this is the first attempt in the world to do such a thing. I'd be very happy to speak with you about all the stuff on the right, but we don't have time right now. So today we're going to focus on the stuff on the left. This is a way to sort of formalize the energy issue that we have. And if you look at the world's total energy usage in the year 2000, it was about 13 terawatts. Most of it fossil fuel derived, a little bit of renewables. And if you do a projection into the year 2050, based on the 2000 numbers, you arrive at a number that's about 30 terawatts. And that's based on assuming the world's population is 10 billion, that we grow at about 2% per year in our GDP growth, and that we get a little more efficient in our use of energy, and so our usage goes down by about 1% per year per GDP. On average, that still means our energy consumption rate goes up 1.5% a year. Do the math, you get 30 terawatts. So the question is, of course, we need to fill the open space with something, hopefully not fossil fuel derived energy, and as well as maybe cut into the existing level of usage. So by the way, more recent numbers in 2010, we're at 16 terawatts, so we're following a trend line that's quite nice. So the question is, how do we fill the open space? So let me now go into photovoltaics specifically, and that would be, of course, one of the prime technologies we'd like to use. So right now there is about 100 gigawatts of installed solar in the whole world. That number has grown recently greatly in the last couple years. So the annual demand in 2012 was 30 gigawatts. So roughly in the last year, we've increased from 70 up to 100 gigawatts. You see the dramatic growth. Where is that growth occurring? Well, you probably guessed it, mainly in China and Germany. In fact, China makes most of the cells and sells them all to Germany. Not all of them, it keeps a lot of them as well. So here's just a timeline of global demand over the last couple years, and here's that dramatic rise. We're kind of at a point of uncertainty right now. There's a lot of uncertainty in what China will do in terms of subsidies for photovoltaics, what global economy will do. So there's various projections of, will this continue on a steep slope, will it level out, or there's scenarios that it could even go back down, hopefully not. By the way, there's a number of online resources you can look at to get these up-to-date numbers. Solar Buzz, PV Magazine, PV Tech, there's probably more. So the question is, why is the problem not solved? There's lots of solar coming. It's not the terawatt level yet, but maybe if you follow this trend line further, you would get to that level. Well, of course, we don't have the technology that meets all of the engineering demands. And there's a number of ways to couch the problem as to what the criteria are you need to meet. And I'm going to list it as 6 criteria that one would like to address. Cost, of course, being number 1. Folded into that is efficiency, stability of the device. And those are probably the 3 that most often you would see. Let me add a couple more to that. Mechanical properties. If you had a lightweight, flexible device, that would make it easier to install. Toxicity, if you're going to go to very large-scale materials, you don't want to use something that will be toxic during manufacturing, during installation. Finally, scalability. We need something that we can create very rapidly. And I'm actually going to focus on that scalability issue in terms of processing speed. And I'm going to make the claim that we need a technology we can produce very, very rapidly. So by the way, why do I choose 6 of these things? Because you can draw a ring in the middle and it looks like a benzene, and that makes me feel good. So why do we need really fast production? And I can use my remote control. Let me just do a physicist back of the envelope calculation. So let's say, for instance, our goal is to meet 30%, 33% of the total 30 terawatts that we'll need by 2050. So we want 10 terawatts. First issue is that the sun doesn't always shine, and across the surface of the globe, the total insolation varies quite a bit. So we have to divide the capacity, the peak capacity, by a capacity factor. That number is typically 10 to 15%. In the desert, it's 22%, something like this. So let's be fairly optimistic and say we're going to put these mainly in the desert. So that's 21%. So we need 50 terawatts of installed capacity. Continue the calculation a little bit more. The issue is that the devices don't live forever, right? There's a lifetime, and then they start to decay, and then they stop working. So you have basically a rate problem that you're producing them, they die, and you have to produce them to reach the 50 terawatts in steady state. So let's do a simple model where they live exactly 30 years and stop. Very simple kinetic model. So our annual production rate to get to 50 terawatts in steady state would be 1.6 terawatts per year. Let's break that down by area. So if we had 20% efficient modules, which is roughly what you buy if you get a silicon module, depends on the company, and is it crystalline or polycrystalline, but roughly 20%, you get 200 watts per meter squared. That comes to 8 billion meters squared per year, 1 million meters squared per hour, which is a kilometer squared per hour. So to solve the problem, or at least a third of the problem, we need to produce a square kilometer per hour of photovoltaic device. This is a big number. It's not unbelievable we could produce something on that scale. If it was pavement or just paint, we could do it. But the problem is that it's a very sophisticated semiconductor device with tolerances of parts per million or less in terms of impurities. So that's the motivation. Let me just outline the rest of the talk. So I'll go into sort of the progress in OPV, where we are now, a little bit how we got there. Then I'll do an overview of the materials and the devices and talk generally about how they work. And then there's 3 topics I want to hit. One is the fundamental thermodynamics, and what are the factors that really control the efficiency of the device. 2 is a little bit of device physics. I'll talk about modeling of the JV curves and how particularly that can be impacted by dark carriers, by impurity-based carriers in the film. And I'll talk briefly about electric field polling as a route to maybe improve the charge transport. And finally, I want to hit on a new topic that we're pretty excited about called energy pooling, which is a sort of biomimetic approach that we're taking. By the way, we have an hour and a half roughly for this whole thing, I'm told. So I don't mind if you interrupt me with questions, and afterwards we'll have a fair amount of time for questions. So a little historical perspective. OPV is actually an old field. The first published paper was in 1958. Came out of Berkeley, so David Kearns and Melvin Calvin. And it was a pretty cutting edge device. First of all, it used 2 different organic semiconductors, this magnesium phthalocyanine and also this tetramethyl phenyldiamine. And in fact, that's what we do today. We use 2 organic semiconductors to ostensibly break up the exciton, the excited state in the devices. There was a problem. They didn't know at the time that both of these materials are essentially p-type. So they had a heterojunction, but it wasn't a true p-n heterojunction. Nonetheless, it worked. What was interesting is they got photo response out to not past 900 nanometers, which even today we have trouble getting efficient response out there. And then what was also interesting is they fabricated it by lamination. So there's no vacuum deposition involved. They simply laminated these 2 layers together. And that's something we actively research today, is laminated production. So it's quite cutting edge, at least for the time. But development continued over the next 60 years. And throughout the 60s and 70s, there were scattered reports of devices based on crystalline materials made of, for instance, tetrazine or rubrene. And then the first polymeric material was polyvinyl carbazole, PVK. You don't call it PVC because that looks like what's in the pipes in your home, but PVK. And Xerox spent a lot of money to invest in that as a xerography material. And some of the original photocopiers were based on polyvinyl carbazole, as well as amorphous selenium. So after that, there were some breakthrough events. The first was in 1986 at Kodak, where the first true p-n junction was made out of an organic solar cell. This was by Qin Tang, who was one of the seminal researchers in the field at Kodak. In 1995 was the development of the bulk heterojunction solar cell, which I'll tell you about in detail. This was a mixture of a polymeric material and also a small molecule, the small molecule being carbon-60, C60. Turns out that that combination yields very efficient charge separation in these devices. Over time, things accelerated, and in here I pop up. So in 2001, I did a postdoc at the University of Linz and worked with some very skilled people and had some luck and wound up increasing the efficiency up to 2.5%, which was immediately broken by a group in Holland who got 2.9%, and things took off after there and have now gone way beyond what we had worked on 10 years ago. But what's encouraging is the recent slope seems to be getting steeper and steeper. And I wouldn't want to do it, but if you extrapolate, you get to some very nice numbers very rapidly. But you know, this has to be a sigmoidal curve and not an exponential. But I just want to point out that the recent numbers are about 12%. And that's the world record is from this German company, Heliotech, based in Dresden. And Mitsubishi Chemical Corporation is close behind them at about 11%, 11.5%. And a whole bunch of universities in sort of the 10% range. So a lot of recent progress. That progress has come largely because of industrial input. So in the last couple years, a lot of big companies have come into the game. They bring a lot of resources. They can provide very pure materials. And that's really accelerated the growth of the field. Just to give you some examples. So I mentioned Mitsubishi and this company Heliotech. Bosch does organic PV, at least up until fairly recently. BASF, largest chemical manufacturer in the world, they're into the game. And then a bunch of smaller startup companies that are spin-offs of, for instance, Northwestern University or Cambridge or Warwick University, a number around the world, Carnegie Mellon University. There are devices in the field. One application is in developing countries that don't have reliable electricity, and this is very important for healthcare. So the maternal death rate in underdeveloped countries is incredibly high. It's thousands of times higher than in our country. And largely it's because they don't have electricity. So this company, 819, as well as a number of other companies, are making little portable PV devices of either organic or other devices, hooked up to a little battery that during the night provides at least a little LED light, and basic medical needs can be met. So besides big energy, healthcare is an imminent need for solar energy. You more or less can buy OPV products. These were produced by a company called Konarka Technologies and were put onto various backpacks. I own that backpack. I forgot to bring it up, but I can bring it next time if you want to see it. These things are okay. They're only about a few percent efficient, and honestly, they're not that attractive when you buy it. But it showed proof of principle that we could manufacture these on large scale. So I need to use the past tense because that company has also gone out of business. PV companies are in flux, and it's a very challenging market, and OPV has not avoided that. The biggest company in the world doing this is, lo and behold, Heliotech, and in their plant, they can, and now their peak capacity is about 3 megawatts, and they're projected to go up to 50 to 75 by next year. I should mention that this is not a solution process, but they're using a vacuum deposition process, which can also be made fairly inexpensive. That is the peak capacity of cells that rolls off of the end of the plant. Year. That is in a year. Correct. Correct. Yes. So what you're going to see is a blade coating technique. It's called a doctor blade. And we're simply going to put an organic solution that has been dissolved in a solvent onto a substrate, which is a microscope slide. So there Robert is pipetting in about 50 microliters of material. And then he's going to push this blade, which is made by the Swiss company Zentner, and the blade will just drag this meniscus of solution across the substrate and create a pretty even film. This substrate is heated at 60 degrees centigrade. That helps dry the film more uniformly, more rapidly. This particular film is very thin because it was made for a field effect transistor, which is only about 30 nanometers thick. So OPV device, we would make it thicker. But the point is that the film is quite uniform over that area. If you look on reflection there, you see the optical quality is quite good. So, and it absorbs in the blue-green, so it has a red color, and there you see the film. So of course, for a solar cell, we would make a much thicker, optically dense film. So there's an idea of the manufacturing that we might do. Just to kind of wrap up the intro part here, the main issue is, of course, cost. And the NREL energy analysis team has gone through pretty detailed pains to come up with these numbers. And they've gone into all of the materials cost of the active layers, the cladding layers, substrates, encapsulation, and whatnot, and made some cost estimates for OPV. And they're actually quite promising. So for a single junction device at 10% efficiency, the cost is about 60 cents per watt. Right? So you do this in terms of peak watt that the module would produce. Now the Department of Energy goal for PV is 50 cents per watt for the module itself. There's another 50 cents per watt for the balance of systems cost, so the total is $1 per watt cost goal. So clearly a single junction at 10% doesn't do it. Tandem junction at 15% does. It gets you just below 50 cents per watt. And if you could get to 20% efficient, which may or may not be through triple junction, that would get you close to 40 cents per watt. So we think this is very promising, and these are some of the lowest numbers you can find for any of the thin film technologies, including CAD telluride, copper zinc tin sulfide, and gallium arsenide, all these sort of emerging technologies. Okay, so that's kind of the non-science businessy part. Let's go into the materials and the devices. So one of the benefits or attractive features of OPV is this broad range of chemical compounds that we could use. virtually an infinite number of materials we can think about. So just to give you some typical examples, this polymer on the left is a polyphenylene vinylene. It's based on this phenyl group here. You guys probably haven't taken too much organic chemistry, but I'm with you. I've never taken organic chemistry, but I just know a few key words like phenyl and thiophene. So these are kind of early generation materials. The band gap is 2 eV. It's a little high for the solar spectrum. So over time, the band gap has been decreased, first by putting thiophenes in the group. So this is poly-3-hexylthiophene. That's one of the workhorse materials. And then more recently, by putting in hetero moieties into the backbone of the polymer, that these things function to push electrons back and forth along the backbone of the polymer. And that's how you can modulate the optical band gap of the structure. So the way these things absorb light is that there are pi electrons that are delocalized around the ring of the benzene or the thiophene, and they become delocalized along the backbone of the polymer. So those are involved or at the core of electronic excitations that absorb the photons that come in. So those are all polymeric materials in blue. We also have these vacuum deposited materials that don't have these long linker chains on the side, so you can heat them up and they won't crack, and they will sublime onto a device substrate. We can also have materials that are low molecular weight, not polymers, but we also dissolve them in solution. Those are solution processable small molecules. Now all of these types of materials are donor materials. They're electron donors. That means they're basically p-type. We need on the other side some n-type. Those are electron acceptors. The variety of these molecules is a lot less. Typically we use carbon-60, the buckyball. That is one of the best electron acceptors we have. Parylene also works reasonably well, but not quite as well. But most of these are derivatives of C60, the most common one being PCBM, which is this C60 with some side chain on here, or for instance ICBA, C60 with these two groups on the end. So those groups on the end will change the electronic structure a little bit, the reduction potential of the fullerene, and that changes the voltage you might get out of the device. More recently, we do have some other materials that act as electron acceptors. They start to look quite promising. Efficiencies 2, 3, 4%, but still a long way to go. So let me give you just a cartoon picture of how these things work. This is far from an accurate physics description, but just gives you a general idea. So light comes in, hits the pi electrons that are delocalized on some segment of polymer. This is a pi conjugated segment, typically 4 to 7 monomers long. There's an exciton that's formed in that segment. That's the excited state. And that lives typically a couple hundred picoseconds, 300 picoseconds. Now what happens is if there's a C60 in the vicinity being a few nanometers or 1 nanometer, there's an ultra-fast electron transfer separating the exciton into an electron on the C60, leaving a positive charge, the hole on the polymer. The important thing is that that charge-separated state lives very long, and its lifetime at room temperature is something like a microsecond. So you have this big asymmetry between the forward transfer rate, which is extremely fast at 50 femtoseconds, 45 femtoseconds, and the backward rate. So that's that asymmetry that allows us to extract charges out of the device and make a functioning solar cell. So just schematically, if we look at the band structure of these things, we can draw HOMO and LUMO levels. That's basically chemists speak for valence band and conduction band. So we form an exciton on one of these materials. And the important point is that you don't create free charges right away. You've got a bound state where you see that the energy of the hole and the electron have collapsed in a little bit. That's the exciton. That has to diffuse or be created near the interface with the acceptor so that we can dissociate it. Now, what happens is there's an intermediate state that I'm going to talk a lot about called the charge transfer state, which is kind of this little hiccup state before we get to full separation of charges that are mobile in the device. And it turns out that CT state, the charge transfer state, is very important. But at any rate, once we have free charges, then we can rely on built-in fields inside the device or some selectivity of electrodes that would be attached to the hole side and electron side of the device and extract the charges out of the device. By the way, the maximum voltage you get out of the device is this effective band gap. It's kind of a cross band gap between the donor material and the acceptor material. It's another big difference between an organic solar cell and a silicon solar cell, where the band gap is defined by the band gap of the silicon itself. Let me just mention the CT state a little more detail. And the first thing is that it's a better idea to draw that whole process as a state diagram as opposed to a band diagram. That helps alleviate confusion between exciton energy and free charge energy, which you really can't put on the same plot. But if you do it as a state diagram, you say there's an electronic excitation up to the first excited singlet state, the S1 state. Then there is a charge transfer event to produce this intermediate, the sort of hiccup state, the charge transfer state. And then finally, hopefully, some free carrier generation. And these processes here are in equilibrium, so free carriers can come back into the CT state and can recombine to the ground state, which would be a loss mechanism. So we want to shut off both of these mechanisms and just produce our free carriers. And just visually, I don't know, the CT state might look something like this. It's a partial sharing of charge between the molecules. Now, when we go to put these donors and acceptors, right, and this is the donor, this is the acceptor, put them into a device, we have two options. We can just make a planar heterojunction where we make a slab of the acceptor and a slab of the donor. And when the charges are separated, they're a very well-defined medium through which they have to transport. That's nice because they can't recombine with each other except right at the interface, but otherwise they can get away from each other. The problem is that the exciton that is initially formed doesn't travel very far. The exciton diffusion length is 3 to 5 nanometers in organic semiconductors, typically. So light that's absorbed far away from the interface, say up here or down here, simply won't make it to the interface, and you won't be able to harness that energy. The way around that is the bulk heterojunction. It's an intimate mixture of the donor and acceptors. Simply mix them in powder in the vial, pour in the solution, mix them up, and go. The advantage here is that there's close separation across the whole bulk of the film, so all the excitons, or 98%, become dissociated into charges because they can always quickly find an interface. But now you see the problem. Once you have the charges, the pathways for actually getting out of the device can be quite tortured, and carrier recombination can be a problem. So both approaches are tried, both work. So the Heliotech 12% device looks something like this with the multi-layer stack of these planar heterojunctions. But Mitsubishi and other companies are using, and universities are using this approach to get 10 and 11%. So either strategy can work, but you should know that there's two different ways to do this. So here's just a typical device. If we take these workhorse materials, P3HT, PCBM, if I took any of you into our laboratory, we could probably have you up and running and making devices in probably a day and a half. After you went through 5 days of NREL safety training, you could be doing devices in a day and a half. And you would spin code films, and you could produce a device at about 4% efficiency pretty easily. So typical voltage, VOC of about 0.6, and typical short circuit current close to 10 milliamps. Just right off the bat. Of course, we can do a lot better, but just as a typical example. If you want to do a lot better, you would need to use a polymer that has a more appropriate band gap. So P3HT's band gap, optical band gap, is 1.9 electron volts, not very well matched with the solar spectrum. So this guy is a lot better. This is the material PTB7. I'm going to talk about this quite a bit. And band gap here is about 1.5 electron volts, or 1.6. And this gets you about 7% efficiency. And in the NREL lab, I think we're about there with PTB7. We've done that. Sarah's done that. One thing I want to point out is that the mixing of the donor acceptor is very important. And how you control the mixing depends on the solvent you use or mixture of solvents. So for instance, dichlorobenzene versus chlorobenzene. And you might add in a co-solvent, which is diiodooctane, which is funny because I think that's the Latin word for God. So if you put a little religion in the device, it works very well. But if you use chlorobenzene in this DIO, you can get a 7.4% device. So there's a little bit of magic in how you actually formulate the morphology, the mixing of the donor acceptor phases. What does that morphology look like? Here's a cross-sectional SEM, and this is kind of a prototype device. We have an ITO substrate. ITO is a transparent conductor. You all have it on your cell phones. We could have several interfacial layers, like zinc oxide is a good interfacial layer. That helps make the electrode selective for electrons. And then we have the active layer material, which is a mixture of donor and acceptor. In this case, we use zinc oxide because it has good contrast in the SEM. And then a top electrode, which is commonly silver, can be aluminum, calcium, depends how we make the device. If you look top down on the active layer with the TEM, you could see some of the nanostructure of the polymeric materials. And one thing you see with this material, with P3HT, is that it grows into a nanofibril structure. So you see these little thread-like features through the film. So this guy self-organizes to some extent. It's not a liquid crystalline material, but it does pack into a linear feature that's about 20 nanometers in diameter and several microns long. We think that's a good thing for charge transport, but not critical. We have lots of devices that don't show that image that work pretty well. We can also, using a TEM, it's possible to filter the energy of the TEM and look for specific elements. And in this case, if we look for the sulfur, which is on that position of the thiophene, then we can see selectively the polymer material versus the fullerene material that has no sulfur. Well, what you see is not too much. It's a fairly uniform dispersion of the sulfur throughout the material. And, but I think if you look carefully, there are some fluctuations and periodicities in there, and there's some data to be extracted. We haven't done that with this image, but we have some better images that we're working on to see what is the distribution of material. So I mentioned that the mixing is very important, and the three-dimensional structure is very important. So there's a lot of technology being developed, a lot of it at NIST in Gaithersburg, but a little bit here in Boulder as well, to really resolve the donor-acceptor components in the material. So this is, again, using energy-filtered TEM, but here they're doing it as a tomographic technique. So what they do is make a little chunk of material, and they spin it around a central axis, and then come in with the TEM and scan across multiple angles, and then reconstruct a three-dimensional image of the material. So here you can see that you can separate out, again, the polymeric component from the fullerene component, and have a pretty good idea of what the thing looks like on a molecular level. Still not quite good enough. The resolution here is something like 3 to 5 nanometers, which really doesn't tell us exactly how polymer and fullerene are aligned at a nanoscale level. So that's something we're also working on. And we're working with the NIST group on using NEXAF's measurements for doing those. And Dan Dessau has been helping a lot with those measurements. Okay, just real quick. And
this is a bulk material?
This is a film that's 200 nanometers thick. So the active layer film, let's go back to the cross-sectional TEM. Thanks for reminding me. This is about 200 nanometers. This is about 100 nanometers. So the whole active layer of the device with ITO is about half a micron. These are truly thin film photovoltaics, right? So amorphous silicon is a couple microns thick, but these are much thinner. That's because of the large absorption cross-section of organic chromophores.
The charges, they have to make their way across 100 nanometers.
That's right. So the mu-tau product in the device, carrier mobility times lifetime, has got to be about 100 nanometers. That's right. Ballpark figure. Really depends on the material. So P3HT tends to have a much better mu-tau product. We can make it much thicker. A lot of the other materials, we have to make them as thin as 80, 90 nanometers to get the charges out. That's one of the big issues. Okay, just want to mention about device architecture. So you can make these in two different geometries where you use a conducting polymer as one of the electrodes, which has a fairly high work function. And that means on the top, you have to use a fairly low work function metal, like calcium. These devices work very well, and most labs will make these devices as kind of a first try. But you can see a problem of using calcium as an electrode. It's very oxygen sensitive. So to bring it outside in the environment, we need to encapsulate it quite extensively. One thing we do a lot at NREL is invert the geometry of the device. And to do that, you put in a buffer layer that only transports electrons. Zinc oxide is an excellent example of that. And so this lines up well with the valence band of the acceptor, and therefore selectively takes electrons from the acceptor into the, eventually through the ITO. Then we can use silver on the other side. And what happens is that silver oxidizes also quite rapidly, but it's very beneficial oxidation in this case. So as it oxidizes, it goes from a vacuum work function of about minus 4.1 all the way down to minus 5 or even lower. So it turns out to be a perfect positive electrode that's already oxidized. It's pre-oxidized, so it's going to do well in air. So for a device that is industrially relevant, that is really robust in air, this is the geometry you'd like to use. Okay, so that's kind of just a rapid overview of OPV. And let me just go into a few specifics about thermodynamics. So one is about the losses that are in the device. And I want to, again, focus on this material, PTB7. We're going to use this as a test case to examine all of the thermodynamics of. So first of all, what's the spectral response? And first of all, these materials have a resonant absorption. So the blue curve here is the absorption of the polymer. And it is unlike an inorganic semiconductor that has a sharp band edge and then is just flat all the way across. But we could define a band gap of about 1.6 electron volts. The red curve here is the response of the fullerene, which does absorb some photons and produces a little bit of current. Overall, about a quarter of the current is coming from absorption of the fullerene as opposed to the polymer. So it's really important to have the fullerene in there, not only to extract charges from the polymer, but to produce current itself. So what I'll do is just do a comparison of an ideal diode, which would have a band gap of 1.6 electron volts, Shockley diode, to the numbers that we have here. Right? So here we have about 15 milliamps per centimeter squared short circuit current, ideal diode about 25. So we've lost 43% over the ideal in terms of current. Voltage, we're at 0.7, ideal is 1.3, have lost another 43%. And fill factor, we're at 0.7 roughly, ideal is 0.9, lost 23%. So overall, we're losing, in this case, 73% relative to the ideal diode. Obviously, a long way to go. So what are the factors that control this? Well, the short circuit current is driven by carrier recombination. And as I'll show, that comes from a combination of kinetics and also the energetics, the band offsets in the device. Now, the voltage, as I showed, largely comes from the band offsets, and that's energetics. A little bit of kinetics in there, but not quite as much. Okay, so I want to talk specifically about that charge transfer state, that CT state, because that's very important. Now, so again, in the state diagram, we absorb into the S1 state, create the CT state. Now, the CT state can itself luminesce. That means that there are effectively two band gaps in the material. There's an absorptive band gap and an emissive band gap. And that changes the thermodynamic calculation. So if you were to do the conventional Shockley-Queisser calculation, that's what you would do for an inorganic device, you have simply one band gap. That would be the band gap, the main band gap of the material. Here we have two. We have an absorptive band gap and an emissive band gap. So when we go through calculations, and if you remember that the ideal photovoltaic device, how you get the maximum efficiency is that all of the emitted light that is the black body spectrum, you assume that all of those photons came from recombination events. And that gives you the minimum possible recombination in the device. That's the black body limit. That's the thermodynamic limit. So, but here we're saying that the emitted photons are coming from a different band gap than the absorbed photons. So what we're going to have to do is integrate the current. So for the absorption, we're going to integrate from the optical band gap of the absorption. But the emitted photons, the band gap changes from E gap to E gap minus delta. So we've changed this integral a little bit here. So that folds into the J absorption in the current voltage curve, and that changes the device JV behavior. So I'll just show you the results. So, well, the free parameter here is the strength of this absorption of the charge transfer state. We'll call that alpha CT, absorption of the charge transfer state. So if you plot, for instance, the efficiency of the device in red versus the alpha CT, what you see is that when you increase alpha CT, it declines, and then there's a minimum and it goes back up. So what's happening? Well, what's happening is that initially you have a little bit of absorption of this alpha CT state, which is re-emitted at a lower band gap. That's a loss mechanism. So as you first kick on alpha CT, you get a loss. But at some point, alpha CT could get so strong that it starts to look like effectively the band gap of the material. And at some point, alpha CT, if it was all the way up there, would mean you have a single band gap material. So you get back to the single band gap limit. The problem is that we currently tend to sit right there at the minimum of these devices. So we have very weak alpha CT state, which we can't get rid of and we can't make much stronger. We are attempting to do both. Through nanophotonics, we can think about increasing the absorption of that state, which tends to be very weak. Or through some chemistry, we can think about weakening that state. So I'm going to talk about the weakening part right now. And the way we think about weakening is pushing the donor acceptor further apart.
Sorry, in the previous formula,
Yes,
you're
yes.
assuming that the CT state does not emit, only absorbs.
No, it is emitting. It is the loss mechanism through its emission.
In the equation in the previous slide,
Oh,
you're setting up
So it's absorbing and emitting. Yeah, sorry, yes. Yeah, so it's in the, wait a second. No, you just absorb from the band gap on up. Yeah, that's right.
So in the intermediate phase, you're assuming that it only absorbs, they only emit.
That's right. But no, it's folded into the absorption as well. Those states also absorb, right? Because actually you integrate from this way up. So you're integrating past the CT state. So it does fold in. So what we think we can do is push the donor acceptor further apart, and that will reduce the coupling of them and reduce, hopefully, the interaction that would lead to the charge transfer state. What we can do is develop materials that have longer side chains, F6, F8, F10. And here the F is the number of alkyl or carbons along the alkyl chain on the side of this fluorine. This is a complicated molecule. It's a fullerene molecule with a fluorine side group. So it's a fluorinated fullerene. Just to throw off my students, one day I want to add an F compound, atomic F in there to make it fluorinated fullerene, but we're not going to do that. So Dave, you guys can work on that. So one thing to notice is that the reduction potential, that is essentially the valence band, is the same within about 20 MeV. We would expect the same voltage from all these materials. We don't quite see that. So we did a simple test run looking at this material with P through HT. Here's the voltage of the normal material that has no linker on it, and we make the linker longer, and we get higher voltage. You get about 50 millivolts of increased voltage. Unfortunately, the current goes down a little bit, so the efficiency also goes down. So we haven't made a better device, but we have increased the voltage, at least up until this F8 material. In other systems, we can go much higher. I'll show you data in a second. We can push the voltage up by about 100 MeV. So what do we think is happening? That longer alkyl chain is reducing the ground state interaction, the CT interaction. That makes a smaller reverse saturation current in the ideal diode equations, and that gives us a little higher voltage. So JS shows up on the bottom here of the logarithm of the voltage. So, and that was work that was, the theory was worked out by a person who's now at Stanford, Koen van der Wal. Like I said, we've done that with other materials. So here is another workhorse polymer we have, PCD-TBT. This is a polycarbazole unit with a benzothiodiazole. That's what the BT is about. This is a lower band gap material that we like to use. And in this case, we jump up about 80 millivolts of voltage when we put in this new acceptor. So we think we can tune the strength of that CT state a little bit. Obviously, we haven't improved the efficiency yet with this technique, but it's something to consider is the distance between the donor and acceptor. It has to be an optimal value. Okay, so let me talk about now a little bit more about the thermodynamics in terms of free energies. And so I mentioned we have this band offset. So here's a more numeric representation. Here's conduction and valence band for the polymer, conduction valence band for the acceptor. It's about a 1 eV band offset. It's a huge loss that we undergo in the device. We could plug this into a simple formulation where we look at the ideal diode equation and see what the loss would be as we increase this band offset. And we're going to call that number delta LUMO, as in the change in the LUMO bands. Those are the lowest unoccupied molecular orbitals. The delta of those LUMOs. So if you plot efficiency versus band gap, and let's say that there's no band offset, so delta LUMO is equal to the exciton binding energy, that's the smallest you could make it, then you get back to the Shockley-Queisser limit. That is a 31% efficient device. And that happens at an optimal band gap of about 1.4 electron volts. That would be an inorganic limit. As you increase the band offset, this number gets larger, and you wind up losing voltage in the device and shifting the maximum efficiency down, as well as the optimal band gap goes to lower energies. Higher energies, lower band gap. So by the way, if you plot optimal band gap versus the delta LUMO, then that number goes up. So it goes from 1.4 all the way up potentially to 2 eV would be the optimal band gap, but you've lost efficiency all the way down to 10%. Point is, we want to minimize this band offset as much as possible, get onto the blue curve, and get up to the 30% level. Now this picture is very simple. It's simply energetics. There's no kinetics here. It doesn't talk about the rates of charge creation or recombination. So to do that, we need a more sophisticated picture. And we're going to use something called Marcus theory, Marcus electron transfer theory. So here is a new version of the band offset picture that has a lot more detail. And I'll skip a lot of it. I'll just give you the main points that we have 3 Gibbs energies that we need to consider. One is the Gibbs energy of the electron transfer event, which is delta LUMO minus this thing called exciton binding energy. Right? That's the Coulombic attraction between electron and hole. There's also a delta G on the other side of the device, because we can absorb into the acceptor, transfer a hole back to the donor, just as we can absorb into the donor, transfer electron to the acceptor. So we have these 2 pathways. And finally, there's a delta G associated with the recombination. So if we have an electron here, a hole here, there's a recombination, we gain delta G in that system. So you can see that as you change the band offset, delta LUMO, that each of these delta G's is going to change, and it's going to be a pretty complicated kinetic scheme that we have to figure out. So let me take that model and put it into a relatively simple kinetic scheme, where we have initially an excited donor, that's the D star, that's where the photon came in and was absorbed, and it's in the vicinity of an acceptor. So we can have a dissociation process to produce free carriers, D plus A minus, or we can have a luminescence to produce the ground state. We've given off a photon here. That's a loss mechanism. We can recombine from the charge separated state to the ground state. Or ideally, the process we want is we can transport electrons out of the device. Each of those processes has a rate constant that we can determine. We measure this rate constant. That's about 300 picoseconds of lifetime. We can measure this time constant. That's about 10 microseconds of lifetime. So the ones that are determined by the energetics are this dissociation rate and that recombination rate. Right? That's determined by the delta G's I just showed you. Now what's the equation that actually determines it? It's Marcus theory, Marcus electron transfer theory. So this theory goes way back and is well understood, at least in chemical systems. And recently we've discovered that it works quite well in solid state organic semiconductors. So just to give you the highlights, there's the rate of reaction, there's the overlap integral between donor and acceptor, and it's squared. And then you have an exponential function of the free energy or the Gibbs energy, delta G. So this looks like a parabola. You've got delta G plus this quantity lambda. And this is squared, so you've got a parabolic function. Oops, I wanted to point out something. So delta is very important. This is the reorganization energy of the system. So what is that? If you take a neutral molecule, put a charge into it, all of the bond lengths will change just a little bit, right? And there will be an energetic shift in the molecule. So that is the reorganization energy upon the electron transfer event. So that is a critical component here, and I'm going to talk about that in a second. Okay, so first of all, is Marcus theory valid? Do we get a parabolic shape to the rate constant? And my colleagues at NREL have given a big hint to the answer, which is basically yes. So what they did was take a series of polymers, combine them with a whole bunch of acceptors, measure the charge transfer rate as a function of delta G, the band offset, and lo and behold, they do get upside down parabolas with a peak position that would tell you what the lambda is, the reorganization energy, comes out exactly where the peak is. So it tells you the theory works, at least qualitatively, and if you believe the numbers, it tells you exactly the reorganization energy, which is about 0.5 electron volts in these materials. So very useful. Okay, I'm going to skip the rates and just cut to the chase. Those are rate constants, but this is basically the performance of the device. So what we can do is take all those parameters and fit them to our existing experimental device. And that is that 7.4% device made from PTB7. And we took the spectra that we know very well, we took the optical densities we can measure, and we fit the reorganization energy and came up with a value of about 0.7. And that gives you a open circuit voltage of 0.7, short circuit current of about 15, and an efficiency of 7.4. So that vertical line is a fit to that 7.4% device. Now we're going to do a hypothetical circumstance of can we change delta LUMO in a systematic way without changing anything else. If we can do that, then things get very optimistic. We can reduce the band offset, increasing the voltage of the device, and the current which is basically saturated because you're absorbing all the photons and extracting all the carriers, you're not losing any current because the kinetics still is working out. And so if you keep doing that at a band offset of about 0.4, you get to 10% efficiency, right? Hypothetical. So I'm a physicist at heart, so I like to play in imaginary land. So let's keep going with that. So let's imagine now that we can reduce the reorganization energy. How would we do this? We would have very rigid materials that as you put a charge on them, the bond lengths don't change. It's a rigid material. I'll talk about that at the end of this slide as well, this section. So let's say we bring that down to 0.3. That allows you to go lower on the delta LUMO and therefore go to higher voltage without losing current in the device before the current starts to drop off. Right? The current drops off because you're in the inverted regime of the Marcus theory, and the rate constant gets very low. Oh, by the way, according to this, the delta LUMO could get close to 0. In fact, it could go below 0. And that's saying that according to Marcus theory, you could suck up some of the thermal heat in the reservoir of the device, use that as an upconversion mechanism. In principle, that's allowed. You could run this as a thermal upconversion device. So anyhow, under that scheme, you get to about 12% efficiency. But here's the bottom line. Now let's go into really good imaginary land and say that both of these materials have an optimal band gap of about 1.4. They're both very dense absorbers. So this is the peak optical density is 1 for both of them. They're both absorbing 90% of the light. So you altogether absorbing 99% of the light. Stick with the very low reorganization energy, and what you get is that you could push this down, the delta LUMO down to 0.2, and get efficiencies approaching 20%. This is not the highest efficiency we could attain. It's the highest we can attain with this material under optimal circumstances. There's still a lot more that we can consider to optimize. But that is one pathway to consider a 20% device that would meet the cost goals that we need to reach. Yeah. Yes?
Does this have to be totally organic? Or is it possible to do some sort of a hybrid cell where you've got an organic and maybe a rare earth or some metal or something that just gives you an energy level you want?
Yep, yep. There are a lot of groups doing hybrid approaches. So you can mix quantum dots with polymers. You can use inorganic zinc oxide. You can use silicon as the donor material. So we've made devices with silicon mixed with one of these conducting polymers, gotten a few percent efficiency out.
Does that change your energetics?
It does, because now the reorganization energy is fully on the organic material, and there would be essentially 0 in the acceptor. It's not that much different because I didn't tell you, but of the two materials, the polymer and the fullerene, this lambda is almost all in the polymer. Fullerene is a very structurally sound material. So the reorganization energy there is, I don't know, 20 MeV, 20 eV, something like that. So 20 MeV, yeah, very small. Okay, so I just want to wrap that discussion by saying we have some candidate materials that might do this. The way you would do this would be to put in lots of cross-linked bonds inside the polymer and make the backbone very rigid. And so we have such polymers that have been given to us by Christine Luscombe's group at the University of Washington. So they are these sort of heteropolymers that have really long conjugated segments where there's lots of bonds on both sides of the backbone. So we don't know the reorganization energy of these guys, but we assume they are a little bit lower, a little more rigid, and we could try pushing the band offsets lower. And by the way, she can tune the band gap across several different spectral windows with those materials. So still working on that. And I'm just going to throw this in there because Dave Walba is in the audience, but we had discussed with him quite a while ago that we could maybe try some of those things here and try putting in extra bonds along the backbone of the polymer and just rigidify the polymeric material. Okay, so I'm running pretty late on time. So I'm just going to hit a few highlights here and talk about some of the device physics modeling that we can do. And so one thing we do is a drift diffusion model. And we're using standard semiconductor equations here. So plug it into the Poisson equation and continuity equations and whatnot. The point is that you can use all these equations just fine, the same you would use for inorganic device, because once the exciton is dissociated, all the rest of the physics is primarily the same. However, to get to the dissociated state, you have to do a kinetic diagram like I discussed, where you have this charge transfer state that acts as a reservoir for the free carriers. So that's included in the model. So no, we've done that, and one thing we've added is that you can put dark carriers in the device. Those are impurity-based carriers that we would like to get rid of, but we know they're in there. So what we can do is we can model the band structure of the device. So this is the electric potential versus position of the device. This is electron and hole densities in the device. And of course, if there's no dark carriers, you have more or less flat bands and uniform field in the device. Well, you have a constant derivative of the field and of the potential. Now, if you start adding in dark carriers, this number C, you start depleting at one of the electrodes over here, and you get non-uniform fields in the device. The issue is that this really happens. So in these materials, we measure carrier concentrations at about 10 to the 16, and that's a significant amount that could bend the band and result in a field-free regime where you get lots of recombination in the device. So this is something we need to avoid. One way we do it is by thermally annealing the device. So that tends to drive off impurities that are at least gaseous, oxygen that is bound. We can release that. But there's other techniques we might consider as well. Okay. And by the way, if you look at the impact of the JV curve of the carriers, that at about 10 to the 16 is when you start to see a loss due to recombination in that dead zone of the device. And at 10 to the 17, you start really killing the device. And just to put some numbers on it, so if you take a device that works just at a nominal 2.7%, 3%, and you've got low dark carriers, if you bring that up to 2 to the 16, you're down to 2%, and 2 to the 17, you're at about 0.5%. So definitely want to get rid of those carriers. One other thing I want to talk about in terms of device physics before I wrap up with energy pooling is the idea of aligning the molecules a little bit better. So these are amorphous materials in the solid state. They're quite disordered, and we would like to organize them a little bit better. And we've been working on a new idea, which is to electrically pole the materials. And actually, Robert has been forging ahead with this technique. We're doing this with field effects transistors for now, not with solar cells. So I'm going to show you the results of field effect transistor measurements. This was an FET that was fabricated here in the CNL lab. And you see these are IDEs with spacings of 10 to 15 microns, something like this, over range of spacings. So what Robert has done is deposit a wet film onto this material and apply an electric field as the film is forming. So align the molecules a little bit better. And here's just a typical OFET performance we can get. We're still getting better at this, but we can get saturation that happens at something like 10 volts VDS and gate voltages in sort of the 10 to 20 range. Maybe you need to go up to 50 volts for some devices. So just typical performance curves for OFETs that we would make. Again, that was made and characterized right here. So just if we apply this electric field pulling business, we notice that there's a couple different variables that control the alignment of the material. Of course, the voltage does it as you would expect. So going from 10, 50, 100, 120 volts, you increase the carrier mobility. Now, if you're coming from the inorganic world, that these numbers are startlingly low in the 10 to minus 4, the 10 to minus 3 numbers. That's where we live in organics, but it's sufficient for most of our devices. Actually, these numbers are a little bit low. We can get up to 10 to the minus 2 or 10 to the 0 in some cases. So basically, with all these geometries we tried of different channel lengths and widths, for the most part, the mobility goes up by a factor of 2 to 5 when we apply electric field. There is a frequency response to this, so this is done under AC. We're using the AC susceptibility of the organic material. So it's not a DC polling. DC would not be strong enough field. But the AC susceptibility can be very high, and we're finding there is a frequency dependence. And we basically haven't maxed it out. So if we go from 30 to 100 to a hertz to 1 kilohertz and 10 kilohertz, we see an improved response. And at this point, we've reached the maximum of our power supply, and we need to buy a new power supply. So there's going to be some resonance somewhere, and we haven't hit it yet.
So Sean,
yes.
So this corresponds to structural ordering. Have you actually looked at XRD or something like that?
We have not. So we've just gotten this to work. So there's lots of things we could try, X-rays, NexApps, even just some light scattering would be useful. Yeah, we really just got started. Another step will obviously to do this on OPV devices, but haven't gotten there yet. But this is already interesting for OFETs, and we think there's much more to go. Okay, I just want to wrap it up with what it will be very brief, exotic concept called energy pooling. And the idea is to basically mimic natural photosynthesis in the sense of having an array of chromophores that would absorb photons and funnel that to some kind of reaction center, right? That's how a photosynthetic complex works. Now, in natural photosynthesis, that happens with one excitation at a time. One chromophore absorbs a photon, funnels it to the reaction center, you get a chemical reaction. We'd like to do that twice at the same time. And the theory behind this has been more or less worked out about 10 years ago by David Jenkins and David Andrews at University of East Anglia. And this is called energy pooling, where you've got two excitons on the arms of the material that can pull simultaneously through a quantum coherent process into the center. And this would give you a doubly excited state. So before I talked about the S1 state, these are S1 states, this becomes an S2 state. So why would you want to do that? Well, if you go back to the thermodynamics, if you remember, we had a delta LUMO that was driving the reaction, and that's essentially a loss in the system. If you have two photons and they go through separate processes, you lose roughly 2 delta LUMO. But now let's consider we've absorbed 2 photons. We've excited a very highly excited state, the S2 state, and now we just have one single charge transfer event, 1 delta LUMO worth of loss. So you've gained 1 delta LUMO worth of energy. And if you just run through the same kind of calculations I showed you before, if you start with a system that has a delta LUMO of like 0.5, and with or without pooling, you see enhancement in the efficiency. Delta LUMO is larger, 0.8, that should be 0.8. You can nearly double the efficiency by incorporating the pooling mechanism. This is all still below the Shakti-Queisser limit, 31% limit. What we don't consider is, could you absorb photons of 2 different frequencies and add those together, frequency adder. If you do that, then all these numbers go up. I haven't done that calculation yet. I'm waiting for a weekend where I have nothing else to do. That's going to happen in 20 years. Or I find a grad student who can do that calculation as well. Okay, so that's the motivation. We haven't done it yet. We don't have the results. We've just gotten started. But we have some very interesting candidate molecules that were synthesized here. So in Dave Walba's group, is a grad student, Nan Hu, who has made this really beautiful molecule. It looks a little bit like the cartoon. You've got a central core receiving group, which looks like a little section of graphene. That's called hexabenzochorinine. And around the edges are ligothiophenes that would act as chromophores. And there's 6 chromophores for 1 central receiver. So we're looking at spectroscopy for this guy, and we see some evidence of energy transfer, but we know that this is not going to be the answer because the energetics aren't quite right. Here, for instance, the HOMO and LUMOs of the arms, but is a good learning molecule. And then just finally, these are recent results from Nan, and I swiped from her presentation she showed 2 days ago, that these turn out to be liquid crystalline materials. So they have very strong responses to electric fields. Nan was able to flip them, I think, a full 90 degrees off the substrate, right? So again, electric field pulling, but in this case, in a truly liquid crystalline material, and you get optical microscopy images tell you that it's truly liquid crystal. We don't know the structure yet. We can guess that it's some kind of columnar structure, some kind of supramolecular structure, but X-ray diffraction is being done right now. Okay, so I've gone already a little bit over time, so I think I'll wrap it up there. And I had 2 more things, but I will skip those and not talk about quantum mechanics and just give you a summary. So first point is we can identify multiple pathways to higher efficiency, things approaching 20%. For instance, if we control the CT state, that will do it. If we make more rigid molecules, that's going to be a good thing. Makes it harder to process the materials because they're less soluble when they're rigid, but that is a design challenge. And then I showed you something where quantum coherence could be very important. And I just want to point out that when you talk about OPV, there's not just a single technology. You have all these different materials, all these different architectures. It's really a universe of possibilities. So that's really great. But until it really proves itself on a large scale, on meters of production per second or kilometers per day, it won't be relevant for global energy. So we obviously have a lot of work to do. Okay, so thanks for your patience in what was a quite long talk, and I'll take your questions. The good thing is I got us very close to 1:30 or 4:30 or whatever time it is. So.
The fraction of people who don't collaborate with Shaheen.
Well, the ones that do, I don't want to hear those questions. So yes, yeah. Please, yeah.
You didn't talk very much about the stability of the materials. Obviously, silicon-based materials, they last 30 years.
Yep.
And it looks like the cost you showed early on with both EVs, they're being down around 60 per watt.
If we could produce them at scale, yes. Yep.
Okay.
Yep.
But how long would they last? Certain current
Mhm.
generations buy some solar cells from the farm that are remember.
Yeah. So a typical lifetime is 2 to 3 years. If we make an average device and we do a pretty careful job with it, that would be a typical lifetime. The highest published result is 7 years, which is from the Stanford group, Mike McGee. And Mike just gave a talk at APS last week, and they've put a lot of effort into purifying the material. And some of the impurities that cause problems are leftover monomers that are in the polymer solution. That's a big problem. The N group of the polymer, if that is not a well-defined group, that can photocleave to produce a defect state. Another thing that can happen is cross-linking of the polymer just under intense UV light. So they've cleaned up a material and got rid of a lot of those processes, and they didn't formally announce it, but they hinted that their device will live 20 years of this one they purified. So it wasn't the Professor McGee himself, it was his grad student, and his grad student was kind of sheepish and said, if you look at the data, it's 20 years, and we hope to publish it. So not an official result, but it looks promising. It all comes down to purity. But of course, to make a very pure material is more expensive. So have you actually gained in the levelized cost of electricity at the end of the day? Yeah, I don't know. Please.
You're putting these polymers under fairly high electric field conditions in operation. I'm wondering how you're taking that into account from the standpoint of energy level shifting, from the standpoint of the stability of the polymers.
Under operation at maximum power point, there's not a very high field in the device. So of the order of 10 to the third volts per centimeter in the device. So relatively small. So the issue is that you operate at maximum power point, which is close to the flat band, close to VOC, which is close to flat band. So yeah. So the devices largely operate by diffusion. And so having selective contacts is very important. And so actually Joe and a number of people at NREL work on improving zinc oxide, improving other oxides to make a really good selective contact. Yeah. What you can do is if you take a JV curve and look at the photo response, you can extract out the carrier generation rate as a function of field. And what you find is that it's largely constant. And that says that you're in a field regime that is small enough that you're really not impacting the exciton dissociation rate. You need to get to 10 to the 4 or 10 to the 5 volts per centimeter. Yeah. I had a couple slides on that. That's called Onsager theory that describes the field dependence of the carrier generation. But yeah, in the working device, we're not there. Yeah.
So how important is the morphology of the bulk convection, or do you think about that? Because you like the liquid crystal structures that want to organize, there's been a lot of work on trying to get crystalline materials.
It's the whole ball game basically. So I showed that cartoon picture, but it needs to be something that on multiple scales is very efficient at dissociating the exciton and getting the carriers out. So one of the theories now is that there are 3 dominant phases in the material, that there is a very amorphous phase where donor-acceptor are intimately mixed, And in that phase, you get very rapid carrier generation because there's an exciton always next to interface. But that's a very poor material for transporting the charges. So beyond that are two additional phases that are a lot more pure, that do the transporting. So in some sense, it would self-organize into kind of three components that separate the behavior of the device, charge generation and transport. The issue is that it's really hard to tell if a given phase or domain is actually pure. If you had 99% donor, 1% acceptor, TEM and NextSAFs and can't really tell us that at present. So that's the issue. Yep.
Just wondering, since the whole idea, I guess, here is you are forming these ideally roll to roll or something, with polymer. So can you have some sort of, or maybe people already do, tunable polymer geometry so that basically, you spin on a layer of, basically you make a graded, kind of like you do dual and triple junction. Basically do as many as cost permits rather than just the.
So for instance, we work on this laminated deposition where you have two layers and you put them together under heat and pressure and they stick together. And that works actually very well. And that's envisioned that you could do that in a roll-to-roll process where you have two different substrates that come off of different rolls, go through a compressive roll under heat and stick them together. In terms of more complicated, lithography,
Just to make one junction, right?
that would be one junction. But no, you could keep going though. You could make multiple junctions. We have made double junction devices by the lamination process. It's a little bit tricky. There's a lot of losses at the tunnel junction. So the tunnel junction is usually the hard part in a tandem device. Zinc oxide can be used. There's a variety of materials that can be the tunnel junction. So this polymer PSS can be part of the tunnel junction. You can use a thin gold layer. You can use nanoparticles. So a lot of different approaches. Graphene's been tried, but it's not a solved problem. There's a lot of effort in NREL on the tunnel junction as well. Okay.
Well, let's thank our speaker one more time. Oh, wait, we've got one more question.
With the vacuum deposited small molecules, can you still form the bulk heterojunction kind of structure by depositing two different molecules at once?
Yeah, and the groups that have worked in that area tried for a long time to get that to work. You just have two crucibles and you deposit simultaneously. In the end, they could not control the morphology really at all and had really bad recombination. So they've gone back to just planar devices. And if you make them very ordered, very pure materials, that works the best. As far as we know, I don't know the exact structure of the 12% device. It's possible that there's some blending going on in there, but at least from the publications from those groups, all that effort died off about 5 years ago, and they went to just planar devices with really good quality materials. It always comes down to purity of materials. Yep. Great, thanks a lot, everyone.
Thanks.
Yep.